So the last couple of weeks we defined what an inner product is, what an inner product space is, and we studied many properties of the inner product. So in this week we will be studying the interaction of this inner product with linear transformations which are defined on the inner product space. We begin by studying the impact of these inner products on linear functionals. So let's begin by recalling what a linear functional was. So recall that a linear functional on a vector space V is a linear transformation T from V to F, where F is the field of scalars. So we have studied these objects in detail. We studied the dual of a given vector space. Nevertheless, it's good to recall in this context what a linear transformation is, because it's useful. So recall that there were quite a few examples which we have already seen. Recall that. So let's see a few examples. Let us look at a few examples of linear functionals as well. So examples. So let's first consider R3. So in R3, let's define T of say x, y, z to be something like say x plus 2i plus 3z. This is one linear functional. This is an example of a linear functional. Another linear functional would be T of maybe T1 of x, y, z is equal to say x comma 0 comma 0. This is another linear functional. Okay, how about some other examples? So example 2, maybe C 0 1 R, the space of all continuous functions on the interval 0 1, and we defined I of f, the integral of f, to be the integral from 0 to 1 f of x dx. And we had checked, or we didn't check, rather we assumed it from the knowledge of a real analysis course that this is going to be a linear transformation. And yeah, so this is another example of a linear functional. Another example is maybe on the same space. Define E of f to be equal to the evaluation functional at 0. So every function f is sent to f of 0. That is another example of a linear functional. In inner product spaces, we have something special. We have some special linear functionals that we can talk about, or rather we can use the inner product to define linear functionals. Remember that the inner product is linear in the first variable and conjugate linear in the second variable. So example, so let me not put this, example 3. So let V be an inner product space. That means we have an inner product at our disposal, and let's fix some vector W, and W be a vector in capital V. Define T V to be equal to the inner product of V with W. So my first claim is that claim T is a linear functional. So let's see, T of V1 plus V2, this is just the inner product of V1 plus V2 comma W. But what is this? This is bilinearity of the inner product of V1 with W plus the inner product of V2 with W. But that is precisely TV1 plus TV2. So the additive property easily gets satisfied. How about T of say C times V? This is for all V1 comma V2 in capital V, and that's what the linearity is about. The additive property is about. T of CV in this case will be the inner product of CV with W, and the linearity property of our inner product tells us that this is C times the inner product of V with W, which is C times TV. So yes, so hence T is indeed a linear transformation and therefore a functional. So let me just directly write it down as a linear functional on V. If you slowly go back to the examples we were looking at, for example, say example 1. In example 1, what was our T? Our T was T of x, y, z. If you go back and check, it was x plus 2y plus 3z, the first example that came to my head. Yes. So T of x, y, z was what? X plus 2y plus 3z. And if we are to treat R3 as an inner product space, this is nothing but the inner product of x, y, z with 1, 2, 3. So ironically, the linear functional which we started off with in the first example turns out to be inner product with the vector 1, 2, 3. In fact, the next example that we considered, T, x, y, z, being sent to say x, 0, 0, this is also the inner product of x, y, z with the vector 1, 0, 0. Let's look at the next example that we considered, I, in example 2. I of f is just the inner product of f comma 1, where the inner product of f comma g is defined to be integral 0 to 1 fg. This is also actually the inner product of the integration operation is inner product of f with the constant function 1. So this tempts us to conjecture that in an inner product space, maybe every linear functional can be realized in this manner. So the conjecture, if we are to conjecture it like this, it's partially true in the sense that on finite dimensional vector spaces, we can certainly say that this is the case. So let me state and prove what is known as the Riesz representation theorem. So let me write it down. Riesz representation theorem. So the Riesz representation theorem says that in a finite dimensional vector space, inner product space V, every linear functional can be realized as the inner product with a fixed vector. So let me write it down. Let V be a finite dimensional inner product space over the field of scalars f. So notice that putting f by default now, f means either the field of real numbers or the field of complex numbers. So they are inner product spaces, either complex inner product spaces or real inner product spaces. This result is true in both the scenarios. So let V be a finite dimensional inner product space and T be in V star. T from V to F be a linear transformation, be a linear functional. Then there exists a vector W in capital V such that TV is equal to the inner product of V with W for all V in capital V. So whatever linear functional you come up with, there is some W in the finite dimensional inner product space such that TV is the inner product of V with W. So let's look at a proof of this particular theorem. So proof is revealing in the sense that it will also give us an algorithm to get hold of one such W. So let's look at the proof. So V is an inner product space. So since V is an inner product space, let V1 to, let me call it V1 prime to Vn prime be an ordered basis of V. So it's finite dimensional, so n be the dimension of capital V. So V1 prime to Vn prime be an ordered basis of capital V. We apply Gram-Schmidt orthonormalization to this. Gram-Schmidt. And then we obtain orthonormalization. And then we obtain orthogonal normalized unit vectors as basis. To obtain, apply the Gram-Schmidt orthonormalization to obtain an orthonormal basis V1 to Vn. So I put the prime in the previous case just to ensure that finally I have V1, V2 up to Vn as a basis. So there is an orthonormal basis V1 to Vn of capital V. Okay, so let's pick some vector V in capital V. For any vector V in capital V, we have, by one of the results we have proved earlier, V is the inner product of V with V1 times V1 plus V, V2 times V2 plus the inner product of V with Vn times Vn. So this is something which we have from the last week's lectures. Now let's look at what is TV. Then TV is equal to T of whatever is written above. But then T is a linear transformation. So in particular, this is just going to be equal to inner product of, I'll write down the final stage directly, considering the fact that we are coming towards the end of this course. The properties of a linear transformation is going to give us that this is not V1, this is V, Vn. So be a bit careful. So even this is not 1, shouldn't be confusing. Times TVn. This is precisely what our linear transformation, the properties of linear transformation will give us. But this is an inner product, and if you look at V, V, inner product of V, V1, that is a complex number, or that is a real number. It's a scalar rather. And TV1, because T is a linear functional, TV1 is also a scalar. So this is a product of scalars. So I can just pull this into the inner product into the second coordinate and write this as V, TV1 bar times V1 plus V, TV2 bar times V2. So notice that whatever is being written inside, they are just scalar multiplication of the scalar TV1 bar with V1, TV2 bar with V2, and finally in the last term it will be V, TVn bar times Vn. Now, by the properties of the inner product, this is just the inner product of V with TV1 bar V1 plus TV2 bar V2 plus up to TVn bar Vn. So let's define W to be this vector. What is W? W is TV1 bar times V1 plus TV2 bar times V2 plus up to TVn bar times Vn. And we can notice that then TV is the inner product of V and W, and that's precisely what we had set out to prove. As you can see, as I was observing earlier, this is a revealing proof in the sense that it is also telling us the procedure to get hold of a W which satisfies the condition that TV is the inner product of V with W. So let's look at maybe one more example and maybe use this technique to maybe a couple of examples. We will use this technique to get hold of the vector with which you have to look at the inner product to get hold of the linear functional. So let T be from, let's look at example in a complex vector space. So C3 to C, let's define a linear functional to be say x, y, z is equal to say 3x plus I, y plus 5z. Let's look at this example. So we can actually guess directly from here what the W would be in the case of this linear functional T, but nevertheless let's do the calculation and see exactly whether we get what we are guessing. So what was the procedure to do that? Let's go back, let's go up and check the W, which I'm going to now put in green, the box. This is exactly the element that we are going to define. So in order to do that, we first need to have an orthonormal basis of our given vector space. So we'll just notice, so this is the C3 has the standard inner product, which is given by inner product of Z1, Z2, Z3 and W1, W2, W3 is Z1, W1 bar plus Z1, Z2, W2 bar plus Z3, W3 bar. So I'll just note that beta, so V1 is equal to 1, 0, 0, V2 is equal to 0, 1, 0 and V3 is equal to 0, 0, 1. This is an orthonormal basis with respect to the standard inner product. Is an orthonormal basis with respect to the standard inner product. But then if you look at the candidate for W, then what is our W? W is just equal to T V1 bar V1 plus T V2 bar V2 plus T V3 bar V3. And what is T V1? T of 1, 0, 0. T, if you recall, was 3x plus IY plus 5z. So this is just going to be equal to inner product T of V1 is T of 1, 0, 0, which is equal to 3 bar times V1, which is 1, 0, 0. And what is T of V2? T of V2 is in the same vein, this is I bar, the conjugate of I times 0, 1, 0. And how about the third one? That is going to be T of V3 bar is 5 bar times 0, 0, 1. But notice that 3 and 5 are real numbers, its conjugate is the same, and the conjugate of I bar is minus I. So this is just going to be equal to 3 comma minus I comma 5. And that's precisely what we were expecting, right? Why? Because if you look at inner product of x, y, z with 3 minus I comma 5, remember that the second vector, the conjugate is what will be contributed. So this is going to be x times 3 bar, which is 3, plus y times minus I bar. I bar is minus I, so minus of I bar is going to be I, so this is just going to be I times y, plus 5 bar is just 5, 5z, and this is precisely equal to our T of x, y, z. So yes, we have managed to get hold of the exact vector from the Riesz representation theorem. Let's look at one more example. So this is the example in P2 of R. So we have already see in the case when P2 of r. Okay, let me just write it down. So example 2. So in P2 of r, consider the evaluation map. Consider E from P2 of r to r given by E of P of x is equal to the evaluation at 0. So recall that this is indeed a linear transformation. In fact, it's a linear functional because it is on to R. Now, let's see, P2 of R has dimension 3. It's a finite dimensional inner vector space. Let's look at the inner product with which we would like to consider P2 of R. So consider the inner product integral of P comma Q as being equal to integral from, inner product of P comma Q is equal to integral minus 1 to 1 P of x Q of x dx. And let's try to get hold of that particular vector, that particular polynomial, which will give us the evaluation at 0. So that is our goal. Okay. So to do that, let's get hold of an orthonormal basis. So we have already done that from the previous week. We can apply the Gram-Schmidt orthonormalization. So to what will we be applying this? We will be applying the Gram-Schmidt orthonormalization to the ordered basis 1x x square to obtain one by root 2, the first one, root 3 by root 2 times x, and the final one, which was not fully calculated but nevertheless left as an exercise, this was root 45 by root 3, the term here, times x square minus 1 by 3. So this is the orthonormal basis that we obtain by applying Gram-Schmidt orthonormalization. So now what is the vector W with respect to which, if you look at the inner product, it will give us the evaluation map. So we know what the procedure is. W is basically E of 1 by root 2 times bar times 1 by root 2 plus E of root 3 by root 2 into x bar times root 3 by root 2 x plus E of root 45 by, it's not root 3, I think it's root 5 by, this is root 8, I guess. Times x square minus 1 into root 45 by root 8 times x square minus 1. Okay, so what is E? E is just the evaluation functional. So 1 by root 2 evaluated at 0 will give you back 1 by root 2. So this is going to be, and the conjugate of a real number is the same. So this is going to be 1 by root 2 the whole square. Root 3 by root 2 times x when evaluated at 0 is going to give us 0. So this term will just vanish. This term will vanish. And finally, E of root 45 by root 8 times x square minus 1 when evaluated at x is equal to 0 will give us minus of root 45 by root 8. So times root 45 by, this is not 1, this is 1 by 3, minus 1 by 3 by root 8 times x square minus 1 by 3. Oh yes, there is a times 3. Some mistake, but yeah, taken care of, rectified. So this will be equal to 1 by 2 times 45 by 3 is 15, which is minus 15 by 8 into x square minus 1 by 3. So in particular, this is just going to be equal to minus of 15 by 8 times x square plus 5 by 8 plus 1 by 2, or 4 by 8, which is 9 by 8. Let me just put it like that. So this is the vector, this is the polynomial which will give us the Riesz representation theorem, the vector with respect to which when you take the inner product, you will get the linear functional. In all these examples, what we were doing was that we were getting hold of the W by getting hold of an orthonormal basis first, and then using that orthonormal basis we calculated what the W is. So there is a strong indicator that this W is very heavily dependent on what the orthonormal basis is. But we will now prove a result which says that the dependence is just superficial, it's actually unique. There is no dependence on the orthonormal basis that we have picked. So let me just write down a proposition for you. So let V be a finite dimensional inner product space and let T be a linear functional let W, okay, let me rephrase it. This is a linear functional. Then there exists unique vector W in capital V such that TV is equal to inner product of V comma W for all V in capital V. We know that there exists at least one such vector by the Riesz representation theorem. What this proposition is telling us is that that vector is necessarily unique. So let's give a proof of this statement. The proof of this statement is by considering the possibility of two such vectors W. So let W and W prime be two vectors in capital V such that the inner product TV is equal to the inner product of V with W1, which is the same as the inner product of V with W2. Suppose we have two such vectors, W1 and W2. This is for all V, right? But then the properties of inner product implies that V W1 minus W2 is equal to 0. This is for again for all V in capital V, because VW1 minus VW2 is VW1 minus W2. That's what I have written down inside. But in particular, this is also true for W1 minus W2. For V is equal to W1 minus W2, we have the inner product of W1 minus W2 comma W1 minus W2 being equal to 0. But this is equal to 0. This is 0 only when the vector itself is 0. But this implies that W1 minus W2 is equal to the 0 vector, which implies W1 is equal to W2. And that's what we had set out to prove. So that is just one vector. The vector W does not depend upon the orthonormal basis at all. Okay, that's quite nice. So the Riesz representation theorem is quite powerful in some sense. We have proved it for finite dimensional vector inner product spaces. There is a version of it for infinite dimensional inner product spaces or Hilbert spaces as well. However, it is not in general true. So for example, one of the examples which was considered above, so let me show it to you as in a problem here, that the example here which I am now underlining in green, the evaluation functional on C01R, that cannot be obtained as an inner product with a vector G, say in C01R. Okay, so this is a problem which I would like to work out. So in the material of this week, the problems will be taken care of in this manner. In the middle of the lectures itself, we will try to address some of them. So let E from C01R to R be given by E of f is defined as being equal to f of 0. Prove that there does not exist a G in C01R such that E of f is equal to the inner product of f with G for all f in C01R. Okay, let's look at a proof of this. Suppose there is one such G. So, proof. Suppose G in C01R be such that EF is equal to inner product of f comma G for all f in C01R. If that is the case, then what we will do is we will construct certain functions fn such that we will end up with some kind of a contradiction. So let's see. So notice that the inner product is given by the integral from 0 to. Notice that the inner product of fg is defined to be the inner product of fg from 0 to 1. This is the inner product with which we are working on C01R. So let's define certain functions fn in the following manner. So let define fn to be, let's first draw the graph of fn and then we'll define what fn is. So this is the Cartesian coordinates here. So let this be 1, 0, again this be 1. And let this be 1 by n. So the function fn is going to be the straight line joining 0, 1 to 1 by n, 0. That will be the graph of the function till here. And from here it will be the 0 function. So let's define it specifically. Fn of x is equal to, notice that this is a function defined on 0, 1, right? That will be the domain here. So fn of x will, what will be fn of x? Let's see, that is going to be equal to, well, it will be 0 for x in 1 by n, 1. That's for sure. Let's see what will be the equation of this line. Y be equal to ax plus b be the equation of this line. At x is equal to 0, this is 1. That would imply that b is equal to 1. And at x is equal to 1 by n, y is 0. So 0 is equal to a by n plus 1, which implies that a is equal to minus of n. So fn of x is just minus of nx plus 1 when x is in 0 to 1 by n. Yes, you can check that this is a continuous function. And let's see, what is it that we are looking at? We are looking at, so we are trying to come up with a contradiction if there exists such a g, right? So let's look at E of fn. Notice that this is just fn of 0. So let me write it to a little to the right here. E of fn in our case is just fn of 0, which is equal to 1. But suppose this is also the inner product of fn with g. So let's see, this is going to be, let's now study what the inner product of fn with g is going to behave like. So we will now use Cauchy-Schwarz inequality here to conclude that the inner product of fn with g, if you look at the modulus of this, this is less than or equal to the length of fn times the length of g. Now, length of G is fixed. Let's call it some number C, and let's see what is length of Fn. Let's look at what is length of Fn square. This is just going to be equal to integral from 0 to 1 Fn square of x dx. So I'll not in fact write down what this is explicitly. I'll just notice that, observe that Fn is 0 in this interval from 1 by n to 1. There is no contribution, so this is just going to be integral from 0 to 1 by n, and there is an explicit expression of Fn which doesn't matter. Let me just write it like that. Just one thing to note is that it is less than 1. So Fn square will also be less than 1. So this is going to be less than integral 0 to 1 by n dx. So this, or maybe I can just compute it. Anyway, it doesn't matter, but let's just, for the sake of completion, let's compute it. What is this going to be? This is just going to be equal to minus of nx plus 1, which is 1 minus nx the whole square, 0 to 1 by n dx, which is equal to integral 1 minus 2nx plus n square x square, 0 to 1 by n. So notice that this is just x minus n x square plus n square x cube by 3 from 0 to 1 by n. This is 1 by n minus 1 by n plus n square by n cube 3. So 3 times n. And this cancels off. This is just 1 by 3. This is the exact value, which is. So what does this mean? This implies that mod of the inner product of Fn times G, this is less than or equal to length of G times length of F, which is explicitly equal to the square root of 3n. But notice that for n large, for n very large, what can we conclude? Norm of length of G by square root of 3n is less than 1. But what is LHS? The absolute value of Fn comma G, what should it be? This is exactly equal to E of Fn, which is equal to the absolute value of Fn of 0, which is 1. So we get 1 is equal to absolute value of Fn comma G, which is less than or equal to length of G by square root of 3n, which is strictly less than 1 for n large, which is a contradiction. This contradicts this contradiction so this is a contradiction. Hence our assumption has to be false. Hence there does not exist G in C01 R such that EF is equal to inner product of F with G for all F and C01R. Right. So let me conclude this video by observing that Riesz representation theorem is of course proved for finite dimensional inner product spaces in this lecture. However, in the infinite dimensional case, it is a bit more subtle. There is a version which is which can be proved. There are many versions, in fact, which can be proved, but we will not go into any of those. Let me stop here.